We're going to start by having a brief discussion about why we do analysis. Why is it important? It has its roots in the idea of calculus, and calculus itself has its roots in the problems that were first asked by the ancient Greeks. They asked a number of problems, and so they asked a number of questions, I should say, and we're looking for methods to solve them. You might have heard of the squaring the circle, or doubling the volume, or trisecting the angle. That's not quite the type of problem I have in mind. The questions that they were trying to answer were more things along the lines of, what is the length of a given curve? In some cases, if you have a straight line between 2 points, it's fairly easy to measure the length. In other cases, it might not be nearly as easy to compute the length. So the Greeks were looking for a precise method to compute the length of, basically any type of curve. Another question that they wanted answered was, what's the area of a certain figure? Again, for certain figures, such as the square of the circle, it was fairly easy to compute the area. I mean, have a square side x, the area of x squared, and if you have a circle of radius r, the area is pi r squared. But what would you do with things that look like this? Some of the Greek mathematicians were able, for some of the curves, such as the parabola, for instance, to derive methods that would allow them to compute the area. Archimedes, perhaps one of the greatest mathematicians of all time, developed this procedure. Let's say that this is the parabola. He would do, roughly speaking, this. He would fill it with triangles and compute the area of triangles. That was easy to do, and then if you knew exactly how many triangles there were, well, you can never get exactly the right amount of triangles to fill this, but you could approximate the area. You might also have heard of this attempt to estimate the value of pi by fitting regular polygons inside and outside a circle. Now, computing the difference in the area between the two has got to be small enough, and so you could eventually potentially use that to come up with an estimate for the number pi. Now, this other method, and forgive my drawing, it's a horrendous drawing here, but this other method basically provided some pretty decent approximations to pi. The challenge there from the Greek mathematician's perspective was to build the regular polygons, not so much to compute the true value of pi. Another problem, which was sort of linked to this one, was the idea of determining the volume of a given solid. For the Platonic solids, the cube, the pyramid, some nice formulas, even for solids that weren't Platonic, like prisms or other types of solids like a sphere, you could fairly easily determine the area, the volume, but for blobs floating in space, didn't know how to do that. We didn't have a protocol, a procedure that would work well all the time. The last question that they were sort of interested in being able to solve, what is the tangent to a line or curve or potentially surface at a given point? Well, if you're looking at the tangent to a surface, it can't be a line anymore. It has to be a sphere. So you imagine something that looks like this. This is your tangent. You're looking for the line that touches the curve at only one point without actually crossing the curve. At a surface, you might be interested in finding the plane which is tangent at that. And in specific cases, for all of these questions, the Greeks had answered. Right? They could compute the area of a circle. And Archimedes showed them how to compute the area of a parabola, say. And they could compute the tangent to a curve. For instance, they knew that the tangent to a circle was going to be the line through a point on the circle, which was perpendicular to the radius at that point. So they had well, eclectic, if you want, or potentially random grab bag of tips and tricks for specific cases. But they didn't have a method that would work for all curves. A lot of their work relied on the geometric properties of the specific object, curve, solid that they were studying. By the 17th century, which is a fair amount of time ago, as far as mathematical discoveries go, but not that long ago in the history of the species, we had methods to solve most of these problems. The methods were mostly due to the efforts of two mathematicians, Newton and Leibniz. Newton was a British mathematician, so Newton and the British mathematicians used a theory based on something called fluxions. I don't even know how to pronounce it. This is not the approach that we use anymore. Right? The fact that most of you will not have heard of fluxions outside of a history course tells you that in a sense, this is not the approach that won out. Leibniz and the continental mathematicians, the mathematicians of continental Europe, used instead differentials. Both methods are equivalent, obviously, but part of the challenge is that the idea of a differential, the idea of an infinitesimal value, a value which was, I quote here, greater than 0, but smaller than any number. That definition sort of rubbed people the wrong way. What does that even mean? Now, Leibniz's approach, as was Newton's approach, completely allowed you to solve these problems. And the only price you had to pay is you had to use an object called a differential or infinitesimal number to get through the solution. And this object was basically undefined. It was some quantity greater than 0, but smaller than any number, and that made no sense. People didn't understand what that might have been, except it worked. Mathematicians do not like these situations. If the results are valid, but the methods rest on unsatisfactory footing, we do not like this. In fact, we spent a fair amount of time formalizing mathematics to avoid situations such as these. Now, there's a certain level below which you can't define things anymore. If you've studied geometry, you've heard about Euclid's 5 postulates, but you've also heard about Euclid's axioms. In Euclid's geometry, the point is not defined. Right? We take for granted that we know what a point is, but you cannot go and define the point. And that leaves you in a weird position. Like, one of the theorems of Newton is that if you have two lines that are not parallel to one another, they will meet at one point. But the point is not defined, and neither is the line. So perhaps you can know the line isn't defined as well. So we imagine that this means something along those lines. But you can imagine a world in which this is meant to be a line, this is meant to be a line, and this is meant to be a point. And intersections is also not a term that's defined. So you could imagine in the same world that intersection might mean that the point here lies on the two lines. So in a sense, the statements, the geometrical statements that say that two lines that do not have the same slope lie or meet at one and exactly one point is the same statement in saying that two points which do not coincide, so don't have the same slope, generate one and only one line. So some people said it's easy, just take differentials as these sort of axiomatic quantities. We don't really need to define. But there was still a fair amount of uncertainty around differentials. People didn't like that. Considered to be undignified of a discipline that started thinking or seeing itself as being like the queen of the science. The problem is that both methods use the concept of the infinite. But it did so in an intuitive fashion. Until very recently, we didn't have a good definition for infinite processes. Before George Cantor, and we'll talk about Cantor a little bit when we talk about cardinality of sets, we didn't even know that there were various types of infinity. You could argue, I guess, that the whole body of mathematics is an attempt by humans to understand infinity. Our brains are finite. Our thinking processes are finite. We are trying to basically step outside of the plane in which we live to understand something which is, well, patently absurd when on the face of it. How long has the universe lived? We have a real hard time accepting that it might have lived infinitely. The Big Bang, while probably cosmologically correct, I'm not an astrophysicist, I can't really speak about these things. The Big Bang, even if it wasn't astrophysically correct, I think would be a necessity for us as a species, because without a Big Bang, the universe would have existed forever. And that's just not an idea that we're comfortable. So what is infinity? Is there a way for us to avoid ambiguities? One of the building blocks of calculus or analysis is to try to, when we try to solve the problems, is to use sequences and to see what their limiting behavior would be when n goes to infinity. It's built into calculus. We don't explicitly usually think of it this way, but this is sort of what's happening. When you compute the slope of the tangent line in calculus, what you're really doing is you start by taking a point which is close to the point of interest on the curve, and you compute the slope of the tangent there. Then you say, I'm going to, at the point come closer, compute the slope of that line. And you let the point go even closer, you compute the slope of that line. And the hope is that if the behavior of the curve is nice enough, if it's smooth enough, these lines eventually will converge to tangent line, and we'll be able to compute the slope. But there's a problem there. In order to be able to determine the slope of a line, we need 2 points. So these points that get closer and closer and closer can never reach the point of tangency, because then we would have only 1 point, and there are infinitely many lines that go through the point. So we always need to have 2 points, which means that these points here, let's call them Q1, Q2, Q3, let's call this one here P. These points Qn approach P. They get closer and closer to P, but they never quite reach P. And so when we write that the Qn's approach P, we're really saying the limit when n goes to infinity of Qn is P. There it is. There's your n going to infinity. What does that mean? What is infinity? Is it a thing in its own right, or is it the absence of a thing? Is it the absence of finiteness? Does it exist in the world at large, or does it only exist on a sheet of paper or on a computer screen or in our heads? It's very confusing, and there's no clear-cut answer. I mean, you can study now transfinite arithmetic, and we've basically taken the realm of the infinite and formalized it so that we can play with it as some kind of mathematical theory, but it's still a little bit like geometry. Euclidean geometry does not represent the real world. We formalized it. The ancient Greeks, well, perhaps not so much the ancient Greeks, but a fair number of people after the ancient Greeks sort of saw that as an almost religious text. Euclidean geometry described the universe. And at some point, some people realized that, hang on, there's a fifth postulate there. The idea that if you have a straight line, which I remind you is not defined properly or exactly in Euclid, and a point which is not on the line, then there is exactly one line going through that point, which is parallel to the initial original line, or exactly 1 point, right, one line through that point which doesn't meet the original. That's not the way Euclid worded the fifth postulate. It's just over years trying to put the postulates on solid footing. People tried to prove the fifth postulate, and one of the ways in which people tried to prove it was to show that it was equivalent to this statement here, which at the time people thought was had to be true, obviously, and hence the fifth postulate perhaps was not a fifth postulate. It could be proven as a theorem from the first four postulates. Well, that wasn't the case, right? The challenge that we have here is how do we know that there are other lines, assuming there are other lines that don't fail, through the point which would also not meet the original line. And you'll say, well, obviously this line will meet here. Look, well, yes, I mean, this is an example of something where this works, but we haven't really defined what a line is in the first place. We just talked about lines. And it said, obviously what they meant was it's in the plane, and a line is what we think of as a line. It's like, well, that's not obvious at all. Right? On the surface of a sphere, such as, too close approximation, the Earth is, lines don't exist, right? So the equivalent of a line on a sphere is called a great circle. The geodesic, it's the path that links 2 points with the smallest distance, the smallest length. So wherever you are, there's going to be a great circle by a point. But there's more than one. I mean, this is one of the great circles, but there'd be also perhaps another great circle right here. You can think of those as the slice of the sphere that you get if you cut it with a plane through the origin and passing through a specific point. If I give you two such points, then there's only one great circle through both of these points. So you see here the parallel with Euclidean geometry. So up until the fifth postulate, this idea that the great circles, the equator, all the meridians on the planet Earth, for instance, play the role of lines, and points play the role of points. Everything is the same. But now you come to the fifth postulate, and the fifth postulate is not true in spherical geometry. If you have a line, a great circle, and a point which is not on the line, perhaps this point here, every great circle through that point will meet the initial great circle in at least 2 points. There are no parallel lines in spherical geometry. That was a bit of a blow. People who thought that Euclidean geometry was the only real geometry, when they realized that spherical geometry is also a geometry. That wasn't the one. The one that really got the ball rolling was hyperbolic geometry. Gauss, Lobachevsky, they're the ones who came up with it. Gauss had found the existence of hyperbolic geometry, the one in which there's infinitely many parallel to a line passing through a given point which is not on the line. He didn't want to publish it. He just thought it was going to be too much of a hassle. Lobachevsky was a newcomer trying to make a name for himself, so obviously he tried to push for it, but it was very obscure. It was like a Russian mathematician, published some of these results in journals that nobody read, or at least very few people read, and it didn't cause too much of a uproar, but it did usher in a revolution in the way we think about things, the way we think about axiomatic systems. Another name associated with that was Bolyai, a Hungarian mathematician. So what we have here is that axiomatic systems can sort of help you expand your understanding of fields. We know so many more types of geometries now that we've formalized the system than we used to. Projective geometry, spherical geometries, various types of hyperbolic geometries, tons of them. Geometry now is a branch of algebra to some extent. You can find geometries based on the transformations that leave certain types of objects invariant, basically algebra. Well, what does that have to do with analysis? People were very weary of having obvious statements, things that couldn't be proved explicitly. They wanted to try to minimize the number of axioms that had to be accepted in a theory. For calculus, what that meant is trying to find a way to remove infinity from the picture. There were other issues. I'll leave you with a quote by Bishop Berkeley, who was trying to undermine the efforts of mathematicians. A lot of the processes that Newton and Leibniz used, as I showed you, required the idea of a limit, and he derided their efforts by saying that their processes required a number to which we approach as close as we want using a sequence of approximations, basically the ghosts of departed quantities. What does that even mean? This definition of the limit here was very, very, very nebulous. Did not like that. That actually wasn't a Berkeley quote. The ghost of a departed quantity, that was a Berkeley quote. But this is just how people defined limits. We didn't like that. This isn't precise. This hasn't really solved the issue of bypassing appeal to infinity. And so a consensus sort of built around the need to formalize things, to define our concepts using, well, definitions. Analysis, I'm going to be doing in this course, is the branch of mathematics that deals rigorously with calculus. Let's try to provide rigor to calculus. Let's see if we can bypass the explicit need to appeal to intuitive concepts like infinity. And that's what we're going to do with this. We're going to learn how to make calculus formal, rigorous. And in the process, we will see how to prove statements, how we only accept a statement as true when it has been proven, either in class or as an exercise, and how we build a succession of intermediate results to prove the types of useful results that we want to be able to use. Eventually, the fundamental theorem of calculus. The founders of this approach, Augustin Cauchy, Carl Weierstrass, and Carl Friedrich Gauss.